record. So basically, you did three homework. Actually, we had 4 homeworks. All of you did 3 homeworks. Homework number 4 still not everyone sent to me. So please send at your earliest possibility. As I told you, we will cancel other homeworks that you were going to do together and prepare it. But what you need to do, you need to make your presentation. You need to make your presentations. You need to send me a review of the papers. Again, there is no deadline for review of the paper, but the earlier the better. We will have many things to do at the end of April. Your presentations are based on schedule like we did it, and some of them will be today. After this, also we will have my lectures. You will have, there will be no lab, definitely there will be no lab tour for experimental lab, but I will try to give some lecture based on experimental measurements, based on PIV measurements. I have slides, I will post it, and I will go through it. Even I'm not experimentalist, it's not my slides, we will do it. Final exam will be based on schedule. If you need, we can extend it, we can move it. It's not a big deal, but it's all the first week of May. Okay, so now that's what we have. So please keep on, stay healthy, and try to survive. And second point, let's do this class. So we have several presentations today. So who is going to be first?
I go first.
Ghadi, you want to be first?
Yeah.
Okay. So if you want to be first, let's thank you. So let's switch to you. I think you can share screen now, and we will see your screen.
Yeah, let me pull up the presentation real quick.
Yes. And again, please excuse all of us for all problems with connections, with everything. Everything may happen. So.
Okay. So, oh, I can't. It says host disabled participant screen sharing, so I can't.
Really? Okay.
Yeah.
So, okay. What? How can I? Do you know how can I enable you?
This is the first time I use Zoom.
Okay. Let me see. Okay. Oh yeah. Okay. What we can do now? I can. Oh yeah. I have option make you host or make co-host. Maybe then allow. Okay. Let me see. Okay. Task start video. Okay. Make host. Make co-host. Allow record. Assign to. Okay. I make you co-host now. Let's try again, please. Does it work? Let's try it now because.
Yeah, it works.
Okay. Now please do it. Yeah. Yeah, then actually I can mute myself. Okay, yeah. So everyone sees the screen now?
Yeah.
I see it.
Yeah.
Okay, very good, very good.
Yep.
Now, yes.
So, given
please speak loudly and proceed. Thank you.
Given the current lockdown, I chose to find uses of turbulence inside of like medicine and all that. And one thing I found is that recently, at least within the last 30 years, there's a lot of studies that came with flows inside of the human body or even animal bodies, like kind of lung function, blood flow, sinuses, and all that. So just a brief introduction. While doing this research, obviously Turbulent covers a lot of things. Either we intentionally try to make it happen, or we naturally find it in like nature, storms, even outside of this planet. We find on Jupiter like the big storm that's it's a big vortex. Also, like I said, flow analysis has been popular for a while, but it relatively recently started gaining more traction in the medical field. All the studies I found regarding blood flow analysis, the earliest one dates back probably to like the 80s, which is relatively kind of new. So in this one, we're going to be looking at the different types of flows, which is mainly going to be laminar and turbulent inside of the circulatory system, since it's the biggest liquid containing system in us. So just a brief overview on this picture of the circulation system. You can see there's a lot of arteries, a lot of veins, just a lot of places where the flow can get disturbed. And usually blood flow is laminar through the system, and it has a parabolic velocity profile where your max velocity is going to be in the middle, and your wall velocity is going to be 0, because as your blood vessels are going to travel through, there's the layer of endothelium that kind of is a bit rough, and so to allow more smooth laminar flow, the blood kind of makes its own boundary layer with plasma. So kind of there's a smooth coat of plasma between the blood pallets and the endothelium layer that you can see on this graph, on this picture. And so that smooth plasma obviously allows for kind of makes it its boundary layer. It's kind of the same concept with a smooth golf ball or a dimpled one. But as we saw in the previous one, there's a lot of turns and a lot of kind of narrowings and constrictions inside of each vein. And so a smooth or a constant laminar flow is not always the case. So whenever it's not the case, could be caused by many things. The main cause would be basically any surface disturbance on the outer layer that might disrupt the layer of plasma separating the endothelium and the flow. And so disturbances can be like fat deposits or plaque that can naturally build up if you have a high cholesterol or just eat bad. Also curvature points, like we saw in the graph before, there's a lot of turning points. Someone like pinches your nerve, that can sometimes do it. And so whenever you have a buildup or a constriction in the artery or vein, that narrows the diameter. And so if you still have the flow coming in at the same speed and the same viscosity, it's going to change your Reynolds number. And coming out of that constriction, you're going to have a turbulent flow. Now, depending on which artery and which vein is going to depend on how big, how severe the turbulence is, since each vein, like if it pumps in or out of the blood, that might change it. I'm not exactly sure, but I know that there's a difference in and out. But basically, whenever you have that constriction, after it passes that, you start seeing start seeing eddies form, and those eddies can cause big problems because they most probably cause stasis to form. Now, stasis is basically the early stage of a blood clot. So in the lower figure where you see the smaller, where it says in parentheses hemolysis, those areas you start having blood kind of build up there, and fresh blood keeps passing over it. And so it would stop moving, it becomes stagnant, and that would rigid it up. Now, that also leads to even more problems because, let's go back to this figure. So whenever you start having stasis or small blood clots next to the plaque formation, the laminar flow coming in, that's like the top half, that's the flow that's still laminar and still at high speeds, would actually push parts of these blood clots. Like it would break off small parts of these blood clots and carry them through the circulation system, which could cause even more damage to other organs. Also, the laminar flow helps transport clotting factors, clotting factor inhibitors, sorry. And so whenever we have a decrease in laminar flow, even though we might think that like the turbulence in engineering applications, we have a lot of instances where you apply turbulence to ensure mixing, like a homogeneous mix between in our system. But in this case, because the nature of the what's it called, clotting factor inhibitors, they tend to stick to the stasis. And so instead of them spreading out into the body, preventing more clotting in different parts, they would just stop, become less efficient. Well, basically the turbulent flow causes, well, there's no benefit to having a turbulent flow in our circulatory system. It's always better to have a laminar one. Now, there are cases, not cases, but there are instances where you might have like a turbulent flow in one of your arteries for a second. And you might feel it as like a heart murmur. That might present as a heart murmur, but they usually resolve. Now, the bigger problems are whenever you have those plaque formations that I showed in this one, because the bigger that plaque or that constriction gets, the bigger the currents, the bigger the turbulence on the other side is. And so more probability of that big piece that's constricting your flow to move around. And if it goes into your heart or somewhere else, that's definitely not good. Other than that, medicine relies a lot on expecting it to be fully laminar, because the way they test for clots is they inject dyes inside of certain veins and arteries and trace where they flow. And so if you would have a turbulent flow, also because of the nature of the dye, because the dye tends to stick to certain platelets, because the nature of the dye, if you actually have the case that we have here where you have a plaque and you have a blood clot or stenosis or a stasis, the dye that they would shoot in would just get stuck in that stasis, even though that wouldn't be the cause of the whole clot. It would just stop doctors from actually researching further and finding where it's at. So having a laminar flow, or ensuring that, or knowing that the circulatory system relies on the laminar flow, has gotten a lot of medical benefits. Does anyone have any questions?
Okay, thank you. Thank you for the presentation. Please, questions? No questions? Okay, let me ask something then. Okay, so basically, thank you for the presentation. Really nice talk, and it's actually nice to see that like every year, like we have this kind of meetings. Every year we have presentations, and there are different students, but very often topics that people select are really quite global. And every year I have presentation about some kind of blood pressure, blood turbulence interaction, some kind of medical applications. Every year I have a presentation about like astrophysical turbulence, about weather conditions, about something related to engines. So basically that's really nice. So in this particular case, so what we realized from you, so do you want to conclude that blood flow should be laminar, right? And turbulence is something that undesired there, right?
Yes. So like normal, what is considered normal blood flow is laminar flow. So a turbulence blood flow is considered an irregular blood flow, and that causes thrombosis and leukocyte adhesion. So it's basically, it could present as a symptom of other cardiovascular problems. So yeah, laminar flow is not, laminar flow is the ideal, and so any presence of turbulence can be indicative of like a bigger issue that might be present causing this.
And if turbulence happens, and when it mostly happens, in arterial blood or venous blood? If you go like to your slide number 2, you have that, for future presentation, by the way, you have really good slides one comment, maybe you can put slide numbers, then it will be easier to say
Okay.
where to go. Yeah, because we also, why we do this presentation, it's all, and paper reviews, it's also practice for your future, for all this, like, yeah, this is a slide. So as far as I understand, so red color corresponds to arteria, right? When blood goes out of heart, and blue corresponds to venous case, right? Or vice versa. Yeah.
No, so yeah, the red is going in, blue is going out.
Ah, red goes.
Yeah. So
Okay, yes,
wherever
yeah,
wherever you might find most of the turbulence. Now, based on the research, the small turbulence is caused by curvatures, and yeah, basically caused by curvatures and branches. They usually tend to resolve themselves, and these are usually found in so like in the intestines, renals, kind of those branchy areas you see on the upper body, liver, stomach, intestines, kidneys, and even the brain. But since the brain is kind of not moving, that you don't find a lot of pinches in that. So the smaller disturbances you find in those high traffic areas, if you want. But the big plaque formations and the big plaque formations, the actually more serious disturbances are found in the aorta or in the artery. So like the ones going straight directed to the heart. Those where you would usually find the most serious turbulence cases in heart disease or in heart problems.
all right. What are the Reynolds number here? Can you estimate Reynolds numbers?
I found it can be like 200,000, but it would depend if it's an aorta or a vein, since the diameter kind of changes and kind of this the flow speed changes. So I can't give you like a accurate answer.
I see. Yeah, then the questions right, you say the we try to avoid turbulent, you want to make a flow laminar. But let me see like this, like typical disease that people face, like it's hypertension, right? When you have high blood pressure. And so what people do with it? So historically, what people did some kind of shot and remove a little bit blood to reduce the flow, right? Historically.
Yeah.
What we do now, we are lucky, we have some kind of pills and we can drink them. And what they do, they make capillaries, veins or capillaries wider, right? So that's to reduce pressure. But when you make capillaries wider, you increase Reynolds number, isn't it?
Make the diameter wider, yeah.
Yes. So
but in I think in the case where you're saying that medicine makes it wider, wouldn't it also drop the kind of, so the whole point is to drop the pressure, so wouldn't it make it bigger but also drop kind of the flow speed?
Velocity, yes, that was my question. So it looks so it looks like when we reduce pressure, you still reduce Reynolds number and make it more laminar. That was my question.
Yeah, there's also cases I couldn't find an accurate graph for it, but there's certain cases where you actually, instead of seeing a parabolic flow, you might see a plane, kind of a plane, but that would happen kind of in smaller brain functions apparently.
Right.
And I didn't find much of it, so that's why I didn't really include it.
Yeah, but that's very good point. So what you plot here, and that is classical Poiseuille profile, right?
Yeah.
It's classical with maximal velocity at the axis, zero at the wall. It's classical parabolic profile. In fact, that is true. Remember when we talk about turbulence, and that we discussed at one of my first lectures, that when you have turbulent flow instead of parabolic profile, you have more steepy flow. Instead of this parabola, you will see like something like very close to the walls, right? You will have something.
Yeah.
So the most of the flow will close to the walls, like power 4, something like this. And when it's like this, when you fly on a plane, it helps because like you increase drag force. And drag force make it more stable. So that people say when you are traveling, and even if you have turbulent flight, in fact, it's safe. Sometimes it's safer than laminar because drag force is growing. Even you are shaking, but in average, it's growing. But for this particular case, what will happen is that if you have turbulent flow, it will mean that near the walls, near the capillary wall, boundary layer will become much more important. So what happens? Boundary layer will control your blood flow. And if you have like really some bad capillaries, if you have bad, what does it mean bad capillaries? It means that you have bad boundary layers of it, right? And so that's true. So as long as you have laminar flow, boundary condition at the walls play less role than even when you have a turbulent flow.
Yeah.
And
well, also,
yep.
I was going to say one just interesting thing about like this application that I found is that since this is found in the human body or like in biological bodies, there are other kind of biological factors in play. So with regular body function, you actually have a change in blood viscosity. So that also affects it because your blood viscosity doesn't stay constant the whole time because you have a lot of your so in this like I said, the endothelium in the medial layer, they tend to secrete some substances into the blood, and so these secretions, and if you add it on top of other bodily like organs that add to the blood, that changes the viscosity of the blood over the system.
All right. So yes, yes, that's true. Yes, so that's the point of writing this number. So yeah, if we were in the class, I would write formula now, but everyone can write down, for instance, that what is Reynolds number is some kind of velocity multiplied by length scale divided by viscosity.
Yeah.
So really, when you change viscosity, you change Reynolds number, and viscosity is a transfer property. It depends on actually oxygen concentration in particular. And definitely during the travel of the stream, oxygen concentration changed from maximal to minimal, right?
So you can have the same kind of vein branch that wouldn't usually get disturbed. But let's say you're in a state where you have a high red cell kind of count or a high white cell count. That might actually just cause it to have a small disturbance, even though in any other case you wouldn't find that.
Right. That's right. And also in the formula for Reynolds number, just realize that it's product of velocity by length scale. In your case, length scale is diameter or radius. Now, if that's what happens. So in fact, when you make your capillary wider, it will mean that your flow will be the same, right? The mass is conserved because we don't like remove blood, we just make it wider. So it will mean that your velocity will be inversely proportional to the surface area, which is a squared of diameter, right? So then Reynolds number will decrease when you make your capillary wider.
Right.
Because velocity will be inversely proportional to squared of diameter of the surface, correct?
Right.
Okay. Yeah, that's it, and that's true. Any more questions, please, from the audience, or chat, or tell, please? I believe still everyone hears us. I hope so.
Yes.
Yeah. Okay. So please, questions.
I have a question.
Yeah, please.
Did you do any research as far as like migraines with this? Because I know migraines are usually like the constricting of blood flow to the brain.
There's one of them. I didn't find anything pertaining to like the human migraines. There's a small one that just says that the way they used to spot turbulence inside of rats is by checking migraines or spasms. But nothing kind of directly related. It's more that what I found is that this is how they used to kind of check that, to make sure to double check that they had they caused the turbulence inside of the rats. It's like it would be a symptom, would be a migraine.
Interesting. Yeah, I suffered from migraines for a long time, so I just didn't know if you had seen anything interesting about that.
Oh.
Well, that's a really good comment. That's also, I should say, my wife has the same problem for many years. But what's curious that I'm not sure in her particular case it's related to pressure, to blood pressure, because like what happened when she had like any like headache, what she's doing, she measures blood pressure, but always has good normal blood pressure. So it's something else there in her particular case. So it's not, maybe it's related to brain, but blood pressure, logically, yes. From fluid mechanical viewpoint, definitely it's related to pressure, even pressure waves, how they go.
Yeah, but in terms of medical studies, I didn't find anything directly talking about it. It's more like a side note in their experiment.
Yeah, interesting. Yeah, I had my blood pressure was always normal. My issue, I ended up being anemic, and when I started to take iron is when my migraines went away. So.
Oh, yeah, my brother had the same, just iron deficiency apparently.
I see. Yeah. Any more questions, please? Well, that's interesting presentations, and actually, it's good that we start with medical interpretation of turbulence, because that's something which is popular now and which will become even more popular with public health crisis, because that is the way how you can apply engineering to medical studies. It becomes very popular to do some medical devices, but you may realize that what I know in terms of what I'm doing in terms of research, what we are doing, what we call computational fluid dynamics, turbulence, it's really very direct applications that people can do. It's employ CFD, computational fluid dynamics, to study blood pressure, any kind of human liquids, how they propagate. Because I know many people start doing research from simulating, say, pipe with with elastic boundary conditions, and that's how they started doing research in terms of capillaries, in terms of heart studies, in terms of blood dynamics and pressure and something like this. So that's direct application. So if you want to switch from engineering to medical engineering, that's the, I wouldn't say easiest, but most straightforward way.
There's also one application of turbulence in the medical field that I know of is there's research about a needleless injection. So right now, for like vaccines or anything, you would inject without a needle, and apparently they would like rely on having it enter it at like a slightly turbulent flow inside of your bloodstream so that it would dissipate quicker. And that's just one application. It's interesting.
That's true. That's true. Again, more questions, please. Well, if no more questions, let's thank our speaker. Let's thank if in the class we just support him. And well, regarding the evaluation of presentations, what I think I did not recognize, I will send you, typically remember I gave you like small piece of papers. What I can do, I will send you just this Word document so everyone who wants can file it. Sorry, I didn't think about this before. I thought we can like vote or send emails, but that will be easiest. I will send it. I will send this forms. Okay, thank you again, Ghadi. Thank you very much. It's so who else is today? I know Ansan was going, right? We had Ansan and Hassan. San, are you there?
Yeah, I'm here.
So let me switch to you, and again I should make you co-host such that you can present it, right? Please take your time.
Yeah, can you see my screen?
Yeah.
Yes, we see. Yeah, just
Yeah,
make full mode if you can.
Yeah.
Yeah, like this.
Yeah. So thanks so much, Dr. Ackerman. Yeah. Good morning, everyone.